take a look at example 3. They say sketch the region corresponding to each definite integral, then evaluate each integral by using a geometric formula. If we look at example 3, part A, the function here is just the function f of x equals to 4, which is a constant function. So we go up here to 4, draw it out. Notice that f of x is non-negative from 1 to 3, which means that that definite integral would actually represent the area under the curve of f from 1 to 3, and that area just happens to simply be the area of a rectangle. We can calculate it using our standard methods. The area is equal to length times width. It has a width of 3 minus 1, which is 2, and its length would be 4. So because f is non-negative, the definite integral corresponds to the area under the curve, which means that the value of that definite integral would be equal to 8. Let's take a look at part B. Here, the function that we're looking at is f of x equals x plus 2. This is a straight line with a y-intercept of 2 and a slope of 1. And we're looking at it from 0 to 3. It's the definite integral. At 3, this function would be at a height of 5. And yet, once again, because this function is non-negative over the interval 0 to 3, that means that that definite integral will represent the area under that curve. So this area would be equal to the value of the definite integral. This happens to be a trapezoid. Some of you might not memorize this, but the area of a trapezoid is the average of the bases. That's a plus b. Maybe I'll call it something different. Let's say b1 plus b2 over 2 times the height of the trapezoid, where this would be the first base. This is of length 2. This would be the value of the second base. This would be 5 times the height of the trapezoid, which would be this dimension right here, which is of length 3. So the area is going to be 2 plus 5, which is 7, halves times 3, which is 21 halves. Therefore, the value of the definite integral from 0 to 3 of x plus 2 dx will also be equal to 21 halves. We have one more. Let's take a look at part C. Instead of calling this f of x equals, let me call this function y equals the square root of 4 minus x squared, and I'll explain why in a moment. To see what this equation looks like, let's go ahead and square both sides. If we square both sides, we would get y squared equals 4 minus x squared. I'm then going to add x squared to both sides to get x squared plus y squared equals to 4. Some of you might recognize this from college algebra, but this is actually the equation of a circle. It's the equation of a circle whose radius is, whose center is at 0, 0, and whose radius would be 2, because 2 squared gives us 4. However, we don't have the entire circle because we have the positive part of the radical. We just get the upper half, and we get the following semicircle. What's important for us is because that region does lie above the x-axis, it's non-negative, which means that that definite integral represents the area under the curve, which is simply going to be the area of a semicircle. The area of a semicircle is 1/2 pi r squared. So this is going to be 1/2 times pi times 2 squared, which is 1/2 times pi times 4, which is simply going to be equal to 2 pi. So the value of this definite integral is given by 2 pi. Some of the properties of definite integrals. If f is defined at x equals to a, then if the limits of integration go from a to a, then that definite integral will have the value of 0. So anytime the upper limit and the lower limit of the definite integral are equal to each other, and the function is defined there, then the definite integral has the value 0. Also, we're able to kind of switch the order from the upper limit to the lower limit by changing the sign of the definite integral. Usually it's always out of convenience. We want the upper bound, the larger value to be the upper bound. The smaller of the two values should be the lower bound. If that's not the case, then you can switch the limits by changing the sign of the definite integral. Let's use this theorem in example 4 to evaluate each of the following definite integrals. Here, we know that sine is defined for all real numbers. And if we're looking at the definite integral from pi to pi, from the theorem above, this should have the value 0. For part B, we want the definite integral from 3 to 0 of x plus 2 dx. To work this one out, we would notice that the lower limit is actually larger than the upper limit, so most likely we want to change this. We can switch that order of the limits by changing the sign of the definite integral to x plus 2 dx. And then from there, the good news is this piece here, we just worked out in the previous problem. We saw from before that the definite integral from 0 to 3 of x plus 2 dx was 21/2. Therefore, this one would be negative 21/2.